So good morning. So here is my course on network for large AI deployment, training, and inference of large AI model in network environment. So this work is joint work between myself and the other members of our team. So basically, this course is on 4 parts. The first one is on the establishment of large AI model in network environment, the design and framework of NetGPT. Secondly, I will give the introduction on the deployment, training, and inference of large AI model in network environment, is specifically on the cloud, edge, user collaboration with a large language model in NetGPT. So thirdly, I will give the introduction on the so-called 10 issues of NetGPT. Finally, the future work, the vision, or the whole framework for network native AI and NetGPT. So the first part, and so why NetGPT here? So why NetGPT makes sense here? What's the key philosophy or key principle of NetGPT? As you can see from this picture, and NetGPT is defined, positioned as network-based generative pre-trained transform and agent large language models. So on one hand, NetGPT is the foundation model of all large language models, all networked large language model for end-to-end approach. On the other hand, NetGPT is the networking interface between all AI agent-based large language model and cloud-based large language model. So the key thought is, as you can see from here, we have so many, up to now, so many cloud-based large language models inside the cloud. And also, on the other hand, we have million, even from now on, billion AI engines. They're here, your mobile phone, your autonomous car, your UAV, and even the robots inside the factory, right? So all of them are the AI engines. So when you implement large language model inside the AI engines, you have the trillion, AI-based large language model. So here the NetGPT is positioned as network interface among all large language models, no matter it's cloud-based or it is AI engine-based. So that's the key point here. That's the key philosophy here. Why NetGPT makes sense? Okay. Before we go into the detail of NetGPT, first of all, we should know something about where the so-called large language model came from. So we have large language model, for example, the ChatGPT. Basically, ChatGPT is consisted of 3 key parts, component: transformer, pre-training, and alignment. I will explain more details on transformer later. And after transformer, we have the training, pre-training, very important. And after pre-training, we have the so-called fine-tuning, supervised fine-tuning, SFT. After that, we have the reinforcement learning from human feedback. We call it ILHF. Basically, how ChatGPT works here and why ChatGPT performance so well is is based on the transformer, pre-training, and alignment. Okay, so if we go further inside the detail of the large language model, as I explained previously, we have pre-training, we have fine-tuning, we have reinforced learning from the human feedback, then we can extend them to the specific domain for specific application, right? And here, let me explain a little bit more details on how the large language model works. First of all, we have the low quality data and something like the internet data and text. Then we input them into the language model. And so after language modeling, we input them inside the pre-trained large language model and for pre-training. After pre-training, we move to the second step. We call it, as I explained previously, we call it fine-tuning. We have the supervised fine-tuning, or we have the scalable fine-tuning based on the high-quality data. We call it demonstration data. And after finishing the step of fine-tuning, we move to the next step. We call it IL, reinforced learning, ILHF, from the human feedback. And here we have human feedback. We call it comparison data. From the human feedback, then we give the score for the output result of fine-tuning. And then we get the reward model. After the reward model, we move to the reinforced learning. And after the reinforced learning, we have the final model here. So all these steps are based on the prompt engineering. So in summary, we have the data as input, then we have pre-training module here, we have the fine-tuning step here, then we have the reinforced learning with the prompt here. And most importantly, here we should pay attention to the scale of the parameters. At the step of pre-training, we have the size of parameters as 1 trillion, with 1 trillion size of the data's parameters. But at the step of fine-tuning and the step of the prompt, ILHF, reinforced learning, and prompt, basically we have the volume size of the data parameters on the order of the 10K, 100K, maximum 1 million. So that's very good, indication for us how to do our work, because we cannot give our training, on the order of 1 trillion. So that's too huge, computing power for us. So that's why basically during our work, we are focusing on the fine-tuning and promoting based on the ILHF. Okay. So here we give some details on the whole transform works. So because how transform works will be closely connected with how our NetGPT design, how our NetGPT will be deployed, how the inference and how the NetGPT will work. So basically transform, I should focus like this way. Before that, I should mention this excellent paper, Attention is All You Need. And just because this excellent paper, a new era has been studied. So transform, basically the key part, no matter it's encoder on the encoder side or on the decoder side, basically the transform is consisted of multiple head attention module, and then we have the feed forward module, and so that's the key component of transform. And then we have this key component placed over each other and with as a stacked layer. So, and if we go inside the key part of the transformer, as I explained, we have the multiple head attention. And if we go further inside the multiple head attention scheme, basically we have the input VKQ value, K, and query. Next, I will explain a little bit of detail on how the multiple head attention scheme works here. And basically, you have the input here, and you have a multiple head attention module here, and you have the querying vector, you have the key vector, and then you have the value vector, and then you with input you have different weight matrix based on the for the Q, for the key, for the V. Then finally you have the attention equation. Attention algorithm works like this way. So basically, how the key part of transform multiple head attention algorithm works here. So that's the key part. That's the key equation here. Okay. So I already explained how the transform works here, and so now for NetGPT, for networked GPT, the key point is how to design networked GPT in a distributed way. So we have some kind of reference here. I believe we are familiar with the so-called the network protocol. For example, no matter it's TCP/IP protocol or it's OS protocol, we have a different layer of protocol. We have network interface, network transport application, or physical layer, data link layer, network transport layer, right? And so for design, for establish the network GPT, we call NetGPT. So basically, we can refer to this kind of the network protocol, and the problem will be changed to how to establish the hierarchical and distribute transformer across the different layer and across the different nodes of the network. So just as this slide shows you, like this way. Okay, so let me give you one successful example. Here the example is NVIDIA Macao, and quite popular device for ChatGPT. So basically, it's as this slide shows you, and basically for each box we have 12 transform blocks placed overlapped with each other over each other. Then we have horizontally we have totally 96 this kind of block are connected to each other. So, but let me explain here. So this system works in a centralized way, not a distributed way. So from now on, for our network GPT, our work is to how to design the network GPT in a distributed and hierarchical way. Okay, so, and because, as I explained, no matter ChatGPT or GPT-2 or GPT-4 or transformer, the key component is so-called multiple attention scheme. So for our distributed hierarchical, deployment, so we can have, because this system will be deployed across the different nodes, right? So here we may have several, attention scheme. Here we can have the merge attention between different nodes. Also, we can have a cross attention across different nodes. Even we can have tangled transform or something like so. So that means attention scheme really has flexibility or to be in deployment across the different nodes. Okay, here is just key parameters for the representative large language model currently popular large language model. Here is just to give you some kind of direct sense how the data volume of large language models are. Okay. So I finished my first part. So let me move to the second part on the concrete deployment, training, and the inference of large AI models is back in the network environment. So that's our just recent work finished and has already published in IEEE network. So basically, we want to deploy large language model in network environment, right? And we call it NetGPT. And so if we consider the approach to deploy NetGPT, basically we have three approaches. First is, we call it offloading large model from the cloud to the edge or to the network node. We call it offloading, approach 1. Second approach is, we have the cloud-based large language model, and we can divide them. We can split them. So we call the large language model splitting. Means that we split one large language models, and we put one part inside the cloud, and we put another part of the large model on the edge node or on the network node, something like that. We call it splitting. And thirdly, we have so-called large language model synergy, means that cooperation between cloud and edge node, means that we can put one large language model inside the cloud, and we can have another large language model implemented on the edge side, on the edge node. So basically, we have these three kind of approaches. And of course, different approach has different advantages and disadvantages. For example, for the offload approach, for the split approach, for the synergy approach, we have the storage requirement, we have fine-tune requirement, also we have inference for requirement, we have transmission latency characteristics. And especially for example, for the offload architecture, of course, we have the biggest storage requirement, but the transmission latency is the smallest. And for the synergy architecture, we have smaller storage requirement, but the transmission latency may be big, may be large. So here we do have several trade-offs between the different approach here. Okay, so first of all, let me introduce the approach, the collaboration between the cloud-based large language model and edge node-based large language model. Here, let me give one example here. So, as this slide shows you, we have the user equipment large language model. We have edge large language models. Also, we have cloud LLM large language models, and we can implement different LLM inside the edge node as well as inside the cloud. Okay, so here our work, we use the GPT-2 for the edge node, and we use Llama 7B as for cloud. And we establish the collaboration between the edge node and the cloud node. So here, just to give you the explanation on the parameter size, volume of two models. GPT-2 and the Llama, both of them are open sourced large language model, and the key parameter for GPT-2 base is 170 million, and for the Llama 7B, the data size is 6.7 billion. So both of them, this kind of data size currently can be implemented inside the portable terminal. For example, your smartphone currently can have this kind of large language model implemented inside the smartphone. So that's why here we choose GPT-2 and the Llama 7B as the representative large language models here for our research. Okay. Now, how the NetGPT works here. So here, let me explain the details here. Okay. So first of all, we have the collaboration between the edge node and cloud, right? So on the cloud side, we have Llama 7B. On the edge node, we have GPT-2. So it's some kind of the cooperation between different kind of large language models, right? First of all, from terminal, from UE, step 1, you should go to the authentication step and on the control plane, and after that you move to the step 2. You should have the resource orchestration, and after resource orchestration you get your resource scheduling, and then you back to your terminal again. And step 4, your terminal will connect with the user plane here, and user plane will first have a concise prompt on the step 4, and after you have your concise prompt, and you move to the step 5. Step 5 is, you move to the computing plan. Step 5, you move to computing plan, and you will get the prompt request or processing. You move to this step. So after step 5, you move to the step 6. Step 6 is you're calling the edge language model. You are calling edge language model here. And after step 6, you move to the step 7. Step 7 is the edge node, edge language model will be connected with the cloud large language model. Then from cloud, you get the comprehensive prompt generation answer, and then from the step 8 you move to the step 9. Step 9 is you have the complete request answer generation. Then finally step 10, your terminal will get the final answer here. So that's how the workflow works here, and how the collaboration between the edge-based large language model and the cloud-based large language model, how the work here. So next slide, I'll give you how the concrete step here explain the previously the full workflow of the collaboration between the edge-based language model and cloud-based language model. So here you can, for example, your terminal want to know the library in Brooklyn and Manhattan of New York City, or zoos in Brooklyn and Manhattan of New York City, the location, the capacity, or service of different library or different zoos. So your terminal sends this kind of prompt to the edge node. Edge language model then generates the prompt and explain the prompt with more details. Then the edge large language model send the comprehensive prompt to the cloud large language model. Cloud language model then generate the answer, the full answer, which library in Brooklyn or in Manhattan is what kind has what kind of service here, or the which zoo in Brooklyn or Manhattan of New York City has what kind of animal there. So the answer finally, cloud language model, provide you the full answer. So that's how the whole system works here. You generate concise prompt, then the edge node explain your prompt with comprehensive prompt, then the edge large language model sent the prompt, the question to the cloud generated the full answer. So that's the whole, the collaboration works here. As one example, corresponding to our previously explained the workflow of the whole correlation between the edge and the cloud. Okay, and also, based on this kind of collaboration, you can have some kind of specific application. For example, you can predict the user behavior in the future according to the previously experience or previous data. So here is just one example how to use the NetGPT to predict the user in the next week or next month, what kind of movie the user will choose, will prefer to watch. So as this figure show you, the NetGPT-based prediction, is much more better than the previously LSTM or GRU-based prediction. The performance is better here. Okay, so also, for networking guys, and we always want to know, from which access point, and we can have what kind of the capacity of in terms of data rate, bandwidth, or the transmission delay. So here, for example, here we have 3 users, and we have 2 cloud data center, and we have 3 access point here, and we have different bandwidth or transmission capacity, and our NetGPT can provide you the solution, the answer, which user choose which access point, and will be connect to which data center. So the NetGPT can provide you this answer. Okay. And here, so I finished my explanation on how the synergy approach means that collaboration between edge nodes and the cloud with different kinds of large language model, how they work with each other. I finish the explanation on that. So now let's move to our approach. Another approach means splitting. As I explained, you can split, separate, you can split, you can separate, you can divide one large language model between cloud and edge right? Or even the base station. So how to divide them, how to split them, that's the question here. So here we have done some work on so-called adaptive layer splitting for wireless large language model inference in edge computing. That means if we have one large language model, we want to split them with one part placed inside the cloud and another part implemented on the edge side. So that's our objective here. So here we have done some work on the adaptive layer splitting. Why here adaptive layer splitting is necessary, as this figure show you. And we have one large language model, very big large language model. We put part of them inside the cloud, and we put part of this large language model on edge, and as well as inside the UE, user terminal device, right? But from the user terminal to the edge, from edge to the cloud, we have the, especially we have the, unstable, fluctuating channel between the mobile user and the base station and edge node, right? So here, the problem is changed to how to design this kind of, how to design the scheme to divide, to separate the large language model between the user terminal and base station, and as well as edge node and cloud. So here is the problem. And here we have used reinforcement learning to design, to solve this problem. So our approach is like this way. So one large models, we placed the higher layer of large models, because as I explained, the large model is based on the overlapped, overstacked transform blocks. We call it a layer of blocks. So here we put the higher layer of large model on the edge and the cloud side, and we placed lower layer of large model inside the user terminal UE. And before the UE and the edge nodes as well as cloud, and we have the wireless channel between them. And any output from the lower layer of logical model will go through the wireless channel with Gaussian noise as well as relay fading effect, right? After the wireless channel, then the signal will be input to the higher layer of logical model. So here, we should design a best method to decide how to split the large language model between the UE and edge node as well as cloud, how to split them, and means that we should decide, make decision how many lower layers will be implemented inside the UE and how many higher layers will be implemented on the edge side or cloud side. So we should make this kind of decision here. Okay, so the challenge here is that we put the lower layer inside the UE and we put the higher layer inside the edge node and the cloud, right? But as we know, the computing capacity of lower layer of our mobile phone, no matter it's smart or not, is limited. Computing power, is limited, and we cannot implement the whole large language model inside the UE, right? Inside your mobile phone. So we should have a limited number of UE, low layer of large language model inside the UE. But but the computing power of the UE in a computer is limited, as I explained. So here we have the trade-off between so-called the cost of computing of UE and the Hu PLL value of the Hu large language model inside the UE, edge node, and cloud. So PLL value is a specific matrix of large language model, means the perplexity value of large model. Basically, PLL decides how the performance of large model is better or not so good, right? So here we have a trade-off between the so-called PLL and the cost of mobile phone, cost of UE. So here, and then we use the reinforcement learning to design the best split point, considering the trade-off between the PLL and the cost of UE. So here we use the reinforcement learning to decide to optimize the best, the most suitable split point here. And so here we use the PPO policy algorithm here. Okay, let's see the performance, how this algorithm performance works here. So basically, we have done the huge simulation, experimental simulation with several, representative open source large language model. Here we used Llama 7B, and also we use we have used the Mistral 7B, and also the IEEE 8 billion. And next slide. And also we use the OpenChat 8B, Llama 2 13B, and the Prim 1B. Okay, so let's see the performance here. Okay, we have, and the left side is for the AWGN channel. The right side is for the relay channel, and the horizontal axis is the number of layers. For example, 2 layer, 4 layer, 6 layer, and 8 layer. The horizontal axis is the PPL value. As I explained, the PPL value means the performance of large language model. Okay, so as we can see, the split. Here the horizontal axis means the split point of the large model. As we can see, for example, for different open source large model, and if we put the 4, for example here, the 4 layer of the large language model inside the UE, and then we place another from the 5 layer to the higher layer, we put on the edge side or inside the cloud. If we split the layer here, we can see that, almost up to the 4 layer, for the AWGN, up to 4 layer, the performance is almost the same performance converged. So it means that here, especially in this case, if we put the lower 3 layers inside the UE, and we put the high layers start from 5 inside, on the edge side, we can have some kind of acceptable performance here. Okay, so the same kind of performance, we had the same kind of performance for the other large language model here. So it means that at least this kind of splitting works here. So it means that if we put a small number of lower layer inside the UE, and we put high layers on the edge side, and we split them. We can have some kind of acceptable total performance in terms of the PPL value here. So means that, of course, here is just first preliminary research here, first preliminary steps here, but at least we have some promising result here. Okay. Also, for different, because we used reinforcement learning with algorithm here to decide the optimal split point between the edge side and the UZ side. Of course, we have different reinforcement learning algorithm for PPO, A to C, DQN, and PPO. So here we can see that PPO, the algorithm PPO works. Works the best. Okay, and this slide just show you the whole general feature or general trend, and the horizontal axis is the noise intensity. The vertical, axis is the split point. The trend is quite clear. If the noise intensity increase, and we should have the split point number increase, means that we should put more layers inside the UE, because as I explained, between the UE and the large language models on the edge side, we have widest channel with the noise, Gaussian noise, and really fading, right? Means that we should implement more layer of the large model inside the UE. That makes sense, right? Okay. Until now, I finished my first two parts, and I move to the third part, the so-called 10 issue of NetGPT. Okay. Basically, in the previous 2 years, and the 6G ANA has been very actively in promoting, in pushing the so-called NetGPT. And from 6G ANA, and they have put forward the so-called 10 issues of NetGPT. And basically, 6G ANA is a global forum that, focuses on the exploration and promotion of 6G network AI-related technology, standardization, regulation, and industry. So it's a global forum focused on the 6G network AI-related topics. And from 6G ANA and the 10 issues has been raised, and according to the different, as I explained, from network, we have a different layer of network, right? And corresponding to those different layer, protocol layer of network, and also 6G has reached the so-called, different issues for different layer of NetGPT. For example, for layer 0, and it's a whole network wide, right? So here we should have the general foundation models for NetGPT. And on top of layer 2, we have the layer 1. Layer 1, we have the wireless engine, and also we have the co-network engine. Also we have the OEM engine, right? So for layer 1, we should have, for the who object or who propose a network GPT, we should have the specific run LM or co-network LM, or also the operation, administration, and manage LM. On top of the layer 1, we have layer 2. Layer 2, of course, we have domain-specific physical layer or MAC layer, sensing oriented large language model, and on top of network NetGPT. Also, we have some kind, for example, the neck slicing, congestion control, or neck planning, neck optimization, neck service orchestration. So means that NetGPT is not just one large language model, could be of the whole framework, and within this framework we can have the layer 0 large language model, layer 1 large language model, for the RAN, for code network, or for the OAM. Also, we have some specific large language models, and within the whole framework of NetGPT. Okay, and so especially different large language model for different layer can be reflected or can be connected to the so-called the distributed hierarchical deployment of the transformer blocks, as just explained previously. Okay, the so-called 10 issues. Let me give a little bit detail on the so-called 10 issues for NetGPT of NetGPT. Of course, it's one. We should make clear the scenario of the requirement of NetGPT, right? What's the scenario? And the key issue, second key issue is we should know the theoretical gap between NetGPT and all kinds of large language models. Issue two, we should have some clear understanding on the performance of large language model. And issue two, we should build up the collaboration mechanism of NetGPT, because as I explained, NetGPT is built up based on the hierarchical distributed so many nodes. Could be the cloud, could be a code network, could be edge node, and even including terminals, right? So also issue 5, it should have finally we should be clear on the distributed deployment of large language model. And issue 6, and they should design the whole architecture of NetGPT application. And issue 7, quite importantly, is the so-called security and privacy issue of NetGPT. And issue 8 is connected with 7, the data governance of NetGPT. And finally, we should give the evaluation and metrics NetGPT with the service level agreement, SLA. And finally, the whole life cycle management of large language models. Okay, so here is the whole picture for the 10 issues as I explained. Issue 1, issue 2, and issue 3, 4, 5, and until the issue 10. The whole pictures how those 10 issues are connected with each other, and how each issues make sense, make a contribution here finally. Okay, so the last part is on the so-called future vision and the future framework for network native AI and NetGPT. Okay, of course, for the future 6G, different key players and even different research have totally maybe different viewpoint or different focuses. But no matter what kind of future NetGPT will be, we believe at least for the 6G, we should have become the new added component or new added feature. We should have the intelligent plan, and we should have the data plan, and we should have some network function plan to work coherently with the data plan and intelligent plan. So also for different plan or for different functionality, we have some kind of the orchestration mechanism to connect them, to make them, work smoothly, especially, how the data plan or net function plan or intelligence plan will be connected with NetGPT. So that will be a very, challenge work or very interesting research from now on. Okay, and currently, around the world, there will be one direction will be quite clear, means that for the next 10 years or for the 6G, there will be so-called so many AI engines here, like robots, driving car, UAV, mobile phone, and so on. So here I just explain one excellent paper here. So means that use the large language model to enhance the capacity, the functionality of smartphone, and implement the large language model inside the terminal. So that's give you one very excellent example here. Means that the large language model can work as smart function with smart function inside your mobile phone and make the smart plan or smart management or smart arrangement. So, and also, from now on, we believe large language models can work as an engine. So large language models is very close connected with engine. Maybe large language model is engine from now on. So the large language models can work for different, requirement for different functionality of engine. So here give you another very good example. And so here, with more details how the large model works inside the engine. As you can see, we have large language model here, and we have action, and then we worked with the environment, interactive with environment, and we have observation, then we have memory, return of the feedback, then we have memory, then we have the prompt. After the prompt, we have feedback to large language model. So means that large language model LLM can be designed, can be implemented inside your AI engine, work as a very key part of the AI engine. Means that from now on, AI engine will be closely work with large language model as one integrated part. Okay. So also, some technique here, and also, for distributed scenario, different large models can have the distributed inference, among different distributed GPU and the workflow here. Okay, so that should be my last two slides, I believe. And as we are quite familiar, last year, ITU has already put the so-called the vision for the future for the 6G and defined the so-called capability or IMT 2030, and based on the vision of ITU on 6G, and one important features is AI-related capability, especially ITU for the 6G vision mentioned the so-called integrated AI and communication, and immersive communication, integrated sensing and communication. So here I think, looking at the 6G, the ITU vision on the 6G, I believe NetGPT works very coherently with this kind of new vision or direction of 6G defined by ITU. And that's my final slides, I believe. And in summary, as a conclusion, we believe for the 6G, large language model or foundation model will be inevitably integrated with 6G and will be deployed among across the network and in a distributed way. So key part is network-based GPT and engine large language models make sense here. And on one hand, NetGPT as a function model of all large language models works here and make all large language models to be connected. On the other hand, NetGPT works as a network interface between all cloud-based large language model and all AI engine-based large language model. So that's the position, that's the key functionality, and that's a key contribution of NetGPT here. So that should be my final slide. And here, let me thank you. Thank you for all your attention here. Thank you.